Hey everyone, and welcome to today's Explainer. We're going to dive into a seriously fascinating topic today, how engineers actually teach machines to make great decisions. And get this, we're going to do it without needing a single complex math equation. If you've ever felt kind of intimidated by control theory or complex robotics, stick around. We are going to completely demystify the whole shebang by looking at literally one of the most powerful decision-making strategies ever invented.
So, let's just jump right in with a question, okay? What do a car's cruise control, a hovering drone, and a deep space satellite all have in common? I mean, on the surface, they seem like vastly different machines facing totally unique challenges, but they all navigate our world and stay completely stable using the exact same underlying concept, a PID controller. Now, I know that sounds highly technical, but at its core, it's really just a method for a machine to answer one basic question. I'm not where I want to be, so what should I do next?
To see how machines answer that, let's start with part 1, the basic control problem. Picture this. You're driving a car. Your target is to drive exactly 60 kilometers per hour. That is where you want to be. But you look down at the dash, and your actual speed is only 55. Immediately, your brain registers that something isn't quite right. There's a clear gap between your target and your current reality.
Well, engineers actually have a specific name for that 5 km/h gap. They call it the error. And the entire job of a PID controller is to take that error, that gap between reality and the goal, and automatically turn it into a corrective action, like pressing the accelerator. And it does this continuously. To manage this perfectly, the controller breaks its thinking down into 3 distinct perspectives: the present, the past, and the future.
Let's start with the present moment. In part 2, proportional.
Forget all the technical jargon for a second. If a machine could talk, its inner monologue for proportional control would simply ask, how wrong am I right now? It's entirely focused on the present moment. It looks at the current error and decides exactly how hard to push back.
And honestly, this brilliantly illustrates how we humans naturally act in our daily lives. Think about it. If you realize you're really far away from your destination and running super late, what do? You walk fast. You've got a large error, so you produce a strong response. But as you get closer, like when you're just a couple steps away from the door, you naturally slow down. Your response is directly proportional to the size of your error. A machine using proportional control does the exact same thing.
But there's a catch. Relying only on the present moment has a fundamental flaw. Imagine you're pushing a shopping trolley toward a line painted on the floor. As you get closer, the error shrinks, so you naturally push less and less. Because of this, you might actually stop the trolley slightly short of the target. Why? Well, because you're so close that the tiny remaining error just doesn't feel important enough to warrant another push. Plus, let's be honest, we're all a bit lazy. Machines do this too. With just proportional control, they get really close to their target, but they'll often just stop slightly short.
To fix that trolley problem, we need the second letter of our controller, part 3, integral, which relies entirely on the past. With the integral component activated, the machine totally shifts its focus. It stops looking only at the present and starts looking backward, asking itself this absolutely critical question: how long have I been wrong? It starts tracking its accumulating mistakes over time.
It's kind of like a teacher taking attendance, right? If a student misses one single class, the teacher probably doesn't worry too much. But if that student has repeated absences, day after day, it accumulates into a very big problem. So the crucial point here is that a tiny speed error of just 1 km/h might not trigger our proportional controller. It just seems too small to worry about right now. But if that 1 km/h error persists for several minutes, the integral component notices. It adds up that error over time and becomes highly motivated to finally fix it.
By recognizing that it's been making the exact same tiny mistake for way too long, the machine finally gives that extra little push. The integral perspective effectively wipes out those stubborn, tiny offsets that proportional control leaves behind, ensuring the machine reaches the exact target, not just, close enough. Which brings us to the final letter of our algorithm, part 4, derivative, which is all about predicting the future.
To stop the machine from aggressively pushing toward the target and just wildly overshooting it, it has to look ahead and ask a forward-looking question. Where is the error heading? Derivative control pays incredibly close attention to how quickly things are changing.
A great way to visualize this is to think about riding a bicycle toward a stop sign. You don't just pedal at top speed and wait until your front tire touches the white line to slam on the brakes, do you? No way. You look ahead, you anticipate your speed, and you start applying the brakes early, well before the target.
This is exactly what derivative control does for a machine. If the system is moving toward the target way too fast, the derivative component acts as an early warning system, applying the brakes to make the motion smooth and completely stable.
So let's put this all together in part 5, from broomsticks to spacecraft. We're going to scale this concept from everyday human intuition all the way up to orbital mechanics.
You might not even realize it, but you actually act as a highly tuned PID controller yourself. Imagine balancing a broomstick vertically on the palm of your hand. If it leans to the left, you move your hand to the left to match it. That's your proportional control acting in the present. If you notice the stick's been slowly drifting left for a while, you recognize that pattern and compensate. That's your integral control, tracking the past. And if the stick suddenly starts falling super fast, you react to that trend before it hits the floor. That's your derivative control, predicting the future. Now, I want you to apply that exact same human intuition to a high-stakes scenario. A satellite in orbit, attempting to perfectly point a camera at Earth. If the spacecraft drifts, the controller kicks in just like your hand balancing that broomstick. The proportional response starts the initial correction. The integral response steps in to fix any small long-term pointing biases so the image doesn't get all blurry. And the derivative response predicts the spacecraft's momentum to prevent wild swinging, ensuring the scientific instruments don't miss their targets and the antennas don't lose contact with Earth.
This simple breakdown right here, it's the ultimate takeaway for today's explainer. It completely demystifies what sounds like a wildly complex mathematical algorithm into a beautifully simple mental model of time. The present asks, how wrong am I right now? The past asks, how long have I been wrong? And the future asks, where is this error heading? By combining these three perspectives, the controller arrives at a single, incredibly smart decision.
So whether it's your car's cruise control, a manufacturing robot assembling tiny electronics, or a spacecraft tracking a distant planet, engineers have successfully taught machines a truly profound lesson. The best decisions aren't just made using what's happening right in front of us at this exact moment. True accuracy comes from combining the present reality with the hard-earned lessons of the past and intelligent predictions for the future. Seeing this fundamental control philosophy mirror your own human intuition really makes you wonder, doesn't it? The next time you adjust your walking speed to catch a train or subconsciously balance yourself on a rocky path, you are using the exact same logic as a deep space satellite. So what other incredible machines out there are quietly mimicking your thought process right now? Keep that in mind as you navigate your day. Thanks for joining me on This Explainer, and keep learning.